Since the 1870s, the gem paperclip has been a single loop of bent wire. It is tempting to look at its century-old, unchanged form and call it a perfect design. But this radar chart shows the hidden reality. Improving one feature, like adding ridges for better grip or using gold so it won't rust, immediately weakens another, like manufacturing cost or structural simplicity. The gem didn't survive because it's the best at any single task. It survived because it manages the most resilient compromise across a web of competing demands. Once a technology completely solves a physical problem, a design's value can detach from its utility. A mechanical watch is functionally obsolete. Your phone keeps better time for free. Yet people pay tens of thousands of dollars for one because they are buying craftsmanship and mechanical soul rather than accuracy. Or consider the QWERTY keyboard. Look closely at the dense mechanical type bars on this 19th century typewriter. This layout was engineered specifically to stop those physical bars from colliding. We eliminated the type bar entirely when we moved to computers, yet 150 years later, we still use the exact same layout. Economists call this path dependence. Once an early decision embeds itself into hardware and muscle memory, it stops being judged on merit. The standard outlives its own reason for existing. The enduring power of an object rarely comes from its physical surface. It comes from the invisible rules and trade-offs locked in during the very first stages of its creation, the concept phase. Take the elevator. For over a century, the engineering challenge was never the physical mechanics of hoisting a heavy box up a shaft. The actual hurdle was human anxiety and impatience. Designers solved this at the concept phase, using psychological tricks rather than mechanical ones. They installed mirrors in lobbies to distract riders and change their perceived wait time, and added closed-door buttons that act as pure placebos to give passengers an illusion of control. True design intelligence often means recognizing that you have to solve for the human mind before you can successfully solve for the physical machine. This explains why highly useful tools often face decades, or even centuries, of delayed adoption. The wheeled suitcase and the dining fork both worked perfectly, yet society rejected them. Even though wheels and luggage had existed for millennia, the wheeled suitcase didn't become normal until the late 1980s. The delay was cultural. Pulling a bag was culturally stigmatized as unmanly. The objection only evaporated when professional flight crews were seen gliding through terminals, which finally normalized the behavior. The fork faced similar resistance in Europe. When a Byzantine princess brought golden forks to Venice around the year 1000, clergy condemned her. The rejection had nothing to do with function. It was entirely about what the fork meant. It was viewed as foreign, seen as excessively delicate, and defying the God-given hand. A design can be functionally flawless and still fail for centuries if the creator does not anticipate and design for the cultural meaning of the object. Sometimes what looks like an aesthetic choice is actually a rigid physical mandate. It's easy to assume the highly stylized, aerodynamic nose of Japan's Shinkansen bullet train was designed purely to maximize top speed or visual appeal. This cross-section reveals the invisible physics driving the shape. Entering a tunnel, a high-speed train compresses air, creating a micro-pressure wave that exits as a sonic boom. To mitigate this, tunnel physics dictate the profile. As speed increases, the nose must grow longer. Despite the train's famous speed, the foundational metric the engineers chose to optimize was unyielding reliability. Decades of operation with 0 passenger fatalities from derailments clearly prove that absolute consistency was always the true goal. The surfaces that look the most freely styled are frequently strict mathematical solutions to invisible problems, locked in during the concept phase. This is why the popular image of a chief design officer sketching beautiful forms is incomplete. Their real job is closer to a goalkeeper, the person who decides what is absolutely non-negotiable from day one. A good product rarely dies from a single bad idea. It dies through 1,000 compromises, where small, individually defensible cuts slowly erode the core concept until nobody recognizes the original intent. When a concept phase decision is defended perfectly, the final design often becomes entirely invisible to the user. You feel it working, but you can't point to it. Look at the rigid geometry of the London Underground map. It's entirely abstracted from the physical stations, a deliberate, useful lie. That distortion isn't an error, it's the core design feature. sacrificing geographical truth to prioritize human legibility and make a complex system instantly readable. Or consider the fire hydrant. The most consequential design decision here is entirely unglamorous. It's the hidden, standardized mechanical threads of the connection point. During the 1904 Baltimore fire, companies rushed in from neighboring cities, only to discover their hoses wouldn't couple to Baltimore's hydrants because the thread sizes didn't match. Over 1,500 buildings burned to the ground, while firefighters stood completely powerless. Today, as AI and real-time rendering make the creation of forms nearly instant, the bottleneck in a product workflow moves back to the concept phase. These historical precedents suggest that design intelligence isn't about the surface detail, it's about the invisible negotiation of constraints at the very start. The most critical decisions are often the ones you can't see once the product is finished. The choices made at the concept phase are the ones that define what a product is allowed to be.